Ever since the launch of the James Webb Space Telescope, we've been treated with fascinating images of the universe like never before. Damn. It even showed us the heavenly bodies of our solar system in a completely new light. We even saw clouds on Saturn's moon Titan, although they are made up of methane, but still cool nonetheless. And we have discovered possible signs of life on an exoplanet only 124 light-years from Earth. Scientists now believe that it is only a matter of time before we find life beyond our planet. That's exciting. However, let's talk about how a recent discovery made by Webb is creating panic amongst the scientific community. Viewers of this channel know that I have reported several times about ancient galaxies found by the telescope that is upsetting cosmologists. They are so ancient that they appear to have formed only a few 100 million years after the Big Bang, contradicting the timeline of the cosmic dark ages. Apparently, the telescope has found more galaxy candidates that could be older than Maisie's galaxy. That would be wild, but what's wilder is an image it took that just made the greatest puzzle in cosmology even more puzzling. Yes, the James Webb Telescope was recently tasked with calculating the expansion rate of the universe, and the results suggest that we need new physics to explain the cosmos. This is the image that did it. You are looking at pulsating stars that reveal the motion of this spiral galaxy 75 million light-years away, called NGC 5584, that suggests the universe is expanding faster than astronomers' leading theory of the universe says it should. The observation is in conflict with an esteemed theory, the Standard Model of Cosmology, that describes how the universe has evolved since the first moments after the Big Bang. So, how exactly is the image creating a stir in our science? The rate at which the universe is expanding, known as the Hubble constant, is one of the fundamental parameters for understanding the evolution and ultimate fate of the cosmos. Imagine the universe is like a big balloon that's getting bigger over time. The Hubble constant is like a special number that tells us how fast the balloon is inflating. Now, scientists have been trying to measure this number using various methods, and the main ways of doing that are distance indicators. Imagine you're trying to figure out how fast a car is moving, but it's too far away to see its speedometer. Instead, you look at how quickly it's getting closer to you. Similarly, scientists look at objects in space, like certain types of exploding stars called supernovae or supermassive stars, way bigger than our sun. These are like cosmic pinpoints in space, and they tell us how fast they're moving away from us, thereby indicating the expansion rate of the universe. 2. Cosmic afterglow. Another way is to look back in time to the very beginning of the universe, like rewinding a movie. Scientists can study the afterglow of the Big Bang, which is like the echo of the universe's birth. By examining this afterglow, they can calculate the Hubble constant based on the early conditions of the universe. The problem is, when scientists use these two methods separately, they get different results for the Hubble constant. This is called the Hubble tension, and scientists are trying to figure out why these methods don't agree. NASA's James Webb Space Telescope provides new capabilities to scrutinize and refine some of the strongest observational evidence for this tension. So, scientists turned the telescope to look at special stars called Cepheid variables. These stars are like really bright beacons in space, but there's a catch when scientists use ground-based telescopes or even the Hubble Space Telescope to look at these stars. Sometimes they see other stars next to them, like when you try to read a sign, but it's blurry because there are other things around it. With Webb's extraordinary infrared capabilities, it can peer through cosmic dust and help scientists see the Cepheid stars much better and not get confused by the other stars nearby. Webb's observation revealed that the earlier Hubble Space Telescope measurements were accurate, although noisier. This means that both telescopes agree on the information they found about the Hubble constant. But here's the tricky part. The universe seems to be expanding much faster than what scientists expected based on its baby picture, aka the cosmic microwave background. Hence, the problem of the Hubble tension still remains. And this brings us to a very important question. What are we missing here? To find the answer, we need to go back in time. Not long after the James Webb Space Telescope began beaming back its images of planets and nebulae from the depths of outer space last year, astronomers, though dazzled by the spectacle, were forced to confront an uncomfortable reality. Something didn't quite fit their existing understanding of the universe. Cut to the present, and we have several months of data received by the telescope that points towards an awkward projection. The need to rethink some of the fundamental tenets governing our comprehension of the universe's origin and evolution. The Standard Model, which is the bedrock of essentially all research in the field, dictates that there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. Yet the data relayed by Webb introduced a jarring twist in this cosmic narrative. It unveiled the existence of exceptionally large galaxies that seem to form with astonishing speed, defying the timelines prescribed by the Standard Model. This finding wasn't a minor discrepancy, and to make matters worse, the conundrum surrounding the Hubble tension remained unsolved. At first, scientists hoped that these discrepancies would be resolved as data got more accurate with more observations. But not only has that not happened, the discrepancies have gotten far more precise, and the recent data from Webb has added salt to the wound. This trend suggests a flaw in the model, not in the data. What compounds this unease is the awareness that over the past half-century, the cosmic model has been patched and amended repeatedly to align more closely with the latest data. While these revisions may have been essential and scientifically sound, in light of the current challenges, they appear as a series of conveniently tailored adjustments. Physicists and astronomers are starting to get the sense that something may be really wrong. The Standard Model of cosmology, which stands as a testament to human intellectual achievement, has its genesis that can be traced back to Edwin Hubble's groundbreaking discovery, the universe's expansion. That's right. In 1929, Edwin Hubble provided the first observational evidence for the universe having a finite age. Using the largest telescope of the time, he discovered that the more distant a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding uniformly in all directions. This observation provided the initial hint of the Big Bang. The Standard Model today holds that normal matter, the stuff that makes up you, me, and planets, and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, occupying roughly 27% and 68% of the universe, respectively. And then comes cosmic inflation, an example of yet another exotic adjustment made to the Standard Model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. The first is that Einstein's general theory of relativity famously makes mass bend space and time. So you'd expect a universe like ours, containing mass, to be overall curved in some way, either in on itself like a ball or out on itself like a saddle. But as we know, it's darn nearly flat. Not only that, but even bits of it, far off in different directions as observed from Earth, have roughly the same temperature, although in an expanding universe, there wouldn't have been time for heat to pass between them to even things out. That seems like a naked assault on the laws of thermodynamics. In 2014, researchers claimed to have seen ripples from inflation imprinted on the cosmic microwave background. But this proved mistaken, and it's not clear what would have made the early universe inflate anyway. Worse, inflation is very difficult to stop creating a multiverse of casually disconnected universes that eternally butt off from one another. Yes, according to most versions of the theory, rather than there being one universe. Ours is just one universe in a multiverse, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. However, there is nothing inherently fishy about these features of the Standard Model. Scientists often discover good, indirect evidence for things that we cannot see, such as the hyperdense singularities inside a black hole. But in the wake of Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint, and it might be time for us to take a radical departure from the Standard Model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time. Any scientific revolution of the sort we're imagining would presumably have comparable reverberations in our understanding of ourselves. For now, we wait and watch what the James Webb Telescope does next. What do you think? Does the Big Bang need a revision? Or is it time to develop a new model altogether? Let me know by dropping in your comments. Thanks for watching, and don't forget to subscribe.